My hope is that these graphs will help to get us thinking, first of all, about the sort of structure of the semester project in the course again, but maybe more importantly than that, to get us to think about how we might do this process of finding finding y-intercepts and x-intercepts, and most importantly, finding maximum and minimum points in situations where we might not have a quadratic formula. So what you can do with this graph, it shows us kind of two different functions. One of them is this green curve. We're going to think of that green curve for today as our revenue function. So it's telling me how many widgets, or not how many, sorry. It's going to tell me if I produce, so I'm going to call this X production, units produced, X. And then my vertical axis here is revenue in, let's say this is revenue in thousands of dollars, or something like that, right? And so this green graph here is the graph of a revenue function, R of X. So if you tell the function how many units you're producing, let's say I want to produce this many units, then the y-coordinate is going to tell me how much revenue, how much sales revenue I make from selling that many units. So that's my revenue function. And we also, on this graph, have a red curve, which is my cost function. This is the total, still called the total cost function, C of X, revenue and cost, measured in thousands of dollars. So if I want to produce a certain number of my product, then this function's y-coordinate tells me how much it's going to cost me to produce that much, right? And so what we can see over here is that if I produce 0 units of my product altogether, then naturally I'm going to make 0 sales revenue, right? Because I can't sell product that I don't actually produce. But it's going to cost me $200,000 to do so. That's probably the amount that it costs to keep the lights on and pay the CEO and all this stuff that we have to pay even if we're not producing any product. Right? And so if I'm making 0 in sales revenue, but it's costing me $200,000 to do it, how much profit am I actually making in the bargain? Say it louder. Negative $200,000. I'm losing money. I'm losing $200,000 in the process. So I've also labeled on here how much profit is being made in that situation, right? And as always, how do we define profit? Where does profit come from? How does it relate to revenue and cost? Where did that negative 200 come from? Yep, profit is revenue minus cost. In this case, 0 minus 200 is where I got that value from. So what I'd like for you to do with this graph, and do this with a group of 3 or 4, is see if you can figure out by dragging this point along, so we can drag this point along the graph to try and pick different quantities to produce, right? So it's not showing us the actual X values here, but it is showing me, the amount of revenue that I would get. So if I increase my production from right there, it looks like our profit is still negative, but not as bad as it used to be, right? If I continue to drag this point a little bit further, we can find places where my profit is positive, right? In this situation, it looks like we're making $300,000 in profit, so this looks pretty good. And of course, if I keep going, eventually that flips upside down again, and cost exceeds revenue, and my profit becomes negative again. So what I'd like for you to try to do with your group is to try to find a point, find where the profit is maximized. And what I mean by that for this graph is, what is the most amount of profit? What's the most amount of profit that we can make in this situation? So that's step 1. I want to give you about 2 or 3 minutes. I don't think it'll take too much exploration to figure that out, but get together with 3 or 4 people and see if you can figure out what is the largest amount of profit that we can make in this situation. So just by experimenting with this graph, you're kind of watching that black number down there, and it goes up for a while, and then it starts going back down. And the biggest that we can make it is right about there. There, I think, 362.5. Is this what everybody had, or does somebody have something different? Okay, so as far as this little applet can show us, that is where it looks like the maximum profit occurs. What about the maximum revenue? Like, where does the maximum revenue occur in this example? Is it more or less? Sorry, do we have to produce more or do we have to produce less to get to the maximum revenue from here?
More.
We have to go up because the vertex of the revenue function, and I haven't given you an equation for this revenue function, so we can't really say if it's a vertex because we don't know if this is a parabola, per se. But whatever is the highest point looks like it's over here, right? So the maximum of the revenue function is different than the maximum of the profit function. So my next question that I want you to discuss is a little bit more conceptual and open-ended. So what I want to know is, at this point of maximum profit, what is the relationship between revenue and cost? So what is going on here? What features of these graphs, what features of the revenue and cost graph are telling me that this is where the profit is largest? Tell me the profit is maximized at this point. So how could I have sort of pinpointed or at least approximated this answer? Like, what is the relationship? What are the green graph and red graph doing at this point that seems like it's important to being able to maximize the profit? That's different from what those graphs are doing in other places. So when I've reached the top of this hill, how are the revenue and cost graphs related together? How are they similar? How are they different? Sort of see if you can figure out what's going on there. So this is a little trickier, but kick a few ideas around for a few minutes. So one completely valid way of understanding why the profit is the largest at this point is that this is the place where the gap in between the revenue and the cost graph, the vertical distance between the revenue and the cost graph, is the greatest, right? It's where they're the furthest apart. It's where the revenue most exceeds the cost. So we get to keep the most of the money that we make from selling our product, right? At all these other points, those graphs are closer together, and so we're able to keep less profit. Or in the bad cases, right, we're able to not keep any profit at all. And lose money in some other places. So that place where the profit is maximized is also a place at which the revenue and cost graphs are the furthest apart. But I want to add one more thing into this picture. So when I say let's think about it from a calculus perspective, if I sketch in a tangent line to the revenue graph at this point, what do you notice about that tangent line? So what do you notice about the tangent line to the revenue graph at this point? Yeah.
That it's parallel with the cost.
It looks like it's parallel to the cost. Here our cost function happens to already be a straight line, right? And so it's kind of, almost really obvious when I look at this picture that that these two lines are sort of going in the same direction as one another, right? This tangent line and this cost line are never going to cross one another. They have the same, what do parallel lines share in common?
The same slope.
They have the same slope. So that seems to be something that's different for this point than it is for any other point that we can find along this graph, right? Every other point we can find, my tangent line and my cost line actually seem like they would intersect somewhere, whether it intersects at some positive value of x, or in some cases it might be at a negative value of x if we were to continue this line backwards, right? They would cross somewhere over here. But at that magic point where my profit is maximized, those two lines are parallel. They have the same slope. So what we might conjecture from all of this is that profit is maximized when the tangent lines to revenue and cost graphs have the same slope. Let me say are parallel and have the same slope. Same slope. So that seems meaningful. That seems important. right? So let's figure out how we could say that using the language of calculus. What is another word for the slope of a tangent line to a function? What are we really talking about?
Derivative.
We're talking about the derivative. That was one of the faces that the derivative wears. I remember, I think it was me that introduced this idea to you all a few weeks ago, right? That the slope of a tangent line is just another name for the derivative. So if we say that the tangent line to revenue and the tangent line to cost have the same slope, what are we really saying in terms of calculus? We're saying that the derivative of the revenue function and the derivative of the cost function are what? Yeah, we're saying that those two things are equal. Right? To write that with notation, we're saying that r prime of x and c prime of x are equal to one another. So let's think about why that makes sense. Coming back to the graph again for a minute, I'm going to add one more annotation to it. And if I look at my profit function, now it's a little bit easier to see, right, that this point that we thought was the top of the profit function really is the top of my profit function. That's as high as my profit function manages to get. So what can we say about the derivative of the profit function at that point? Let me put the tangent line into that one also. So what's going on with the tangent line to the profit function at that place where the profit function is being maximized? Right there. So the revenue and cost graphs have the same slope. What slope does the profit function have?
0.
0. How do we know it's 0?
Is this the vertex?
It's the highest point of the profit function. And what is its tangent line doing at that point? What kind of a line is its tangent line?
Horizontal.
It's horizontal. And what's the slope of a horizontal line?
0.
0. Perfect. Tangent line is horizontal. That means its slope is 0. And so this means that the derivative of the profit function, if we call it p, the derivative of the profit function is equal to 0. So how does all of this stuff sort of come together? Right? We want to maximize profit, find the place where the profit function reaches its maximum value. That means we want to look for places where the derivative of the profit is equal to 0. But on the other hand, profit is revenue minus cost, right? And so if I have the revenue function and the cost function, I subtract them to get my profit function. But if I take the derivative of a difference, it's the difference of the derivatives. So if I take the derivative of r minus c, it's the derivative of r minus the derivative of c. But if r prime minus c prime is equal to 0, that means r prime is equal to c prime, just by adding c prime to both sides. So that's why we're seeing all of these features happening at the same time, simultaneously, right? At this place where my profit is maximized because this is the only place in this example where the derivative of the profit function is equal to 0, because that's the one place where the tangent line is horizontal. You told us at the beginning of the hour that the vertex, or the sort of the highest point of a graph, is a place where the graph switches from increasing to decreasing, or decreasing to increasing, where the derivative switches from positive to negative or negative to positive. That's happening on my profit function right here. Because over here, my profit function is increasing, so its derivative would be positive. On the other side, my profit function is decreasing, and so its derivative would be negative. And so at that magic point in between, its derivative is neither positive nor negative, it's 0. But when the profit function has derivative 0, that must mean that the revenue and cost functions have derivatives equal to one another. And that's what's happening when we look at the revenue and the cost graphs above it here, right? The revenue graph is parallel to the cost graph at that point. And from a practical perspective, and this is where we'll finish, from a practical perspective, what this means is if I'm currently producing this number of widgets, I'm just going to sort of eyeball this and say this looks like it's 75. So if my current level of production is 75 widgets, producing 75 per month, then what this is telling me is if I decide to change my production, if I produce just one more widget and bump this number up just a tiny little bit, I'm going to make a little bit of extra sales revenue according to the slope of this line. It's going to tell me how much more revenue I'm going to make. But I'm also going to have to pay more in cost according to the slope of this line. And those two numbers are going to be exactly equal to one another. I'm going to make exactly as much more in sales revenue that it's going to cost me to produce that thing, and so they're going to wash out. I'm not going to make any extra profit because I'm going to have to pay as much as I'm going to earn in sales revenue for making even just one more unit. Same thing with decreasing. If I decide to produce one less unit, I'm going to give up a little bit of sales revenue, but I'm also going to save a little bit of cost, but those numbers are also going to be equal, right? I'm going to lose out on exactly as much revenue as I'm going to save in costs, and so it all washes out. So that's why this gets to be the maximum, right? It doesn't make sense for us to either increase or decrease production from a profit perspective, because the profit, infinitesimally, if we zoom in on that point, the profit is not actually going to change up or down if we increase or decrease our production.